should be the minimum value. So I hope you got some sense of it actually. Well, I hope you got some sense of it. I'm not doing the more messy calculation. That the key thing was convincing you that why this is a surface area. Okay, and in this surface area we spotted a problem that it depends on two variables. That means you need to get rid of it, one variable, and in order to get rid of one variable, you need a new equation actually, which must be given in the form of some information actually. So figure out that equation. You know, make a function of one variable, compute its critical point, and try to find its nature actually. So we found, for example, second order derivative, substituted, and turns out to be, this turned out to be minimum actually. Okay. So let's get to an interesting problem which says that imagine you have a parabola which is symmetric about, say, y-axis, and it has an equation, say, y square equal to 2x. And you have a point that has you have a point in this space, for example, a point 1, 4. Okay, so this is a point. So I have a point, say, 1, 4. That is, for example, here. Our task, so this problem says us to find a point on the parabola, okay, any point on the parabola that is closest to this point actually. That is closest to this point. For example, so if I, for example, compute, in other words, which point on the parabola is going to have a minimum distance between this point and the point on the parabola. So if I choose this point, for example, that's a huge distance. Any other point would be a big distance. So the minimum should you know, the closest point to this point 1, 4 should somewhere live here. Okay. So I don't know precisely what are the coordinates of it. So let's call them x, y, and say this distance is distance d actually. And our task is to minimize this distance. For what value of x and y this distance between the point 1, 4 and the point on the parabola would be minimum. So what would be the distance between these 2 points? So you can use the distance formula. The distance formula would go like x minus 1 square plus y minus 4 square. This is what is really the distance. Okay. Now, what we will like to do, we will like to say that for what value of x and y d is minimum. So we want to minimize the d. But we are again facing the same trouble, that this d depends on 2 variables. So it should depend on 1 variable. The question is, how can I get rid of 1 variable? So the trick is really that as we know that this xy lives on y square equal to 2x, so it must satisfy this equation. It must satisfy this equation. So y square should be 2x. And if this is the case, then from this I can deduce that x is y square upon 2. So this is what is the value. And now, for example, if I substitute this distance d here, okay, so it's going to be y square upon 2 minus 1 square plus y minus 4 square. Now this d is a function of y. So what we like to do, we like to find a y for which this d is minimum. Okay? We want to find a y for which this d is minimum. Now, here's the interesting point. If I wish, I can, for example, minimize this function. Well, not a big deal. But I'm using a shortcut actually. That shortcut is that instead of minimizing this, let's minimize the square of the dy. Y square upon 2 minus 1 square plus y minus 4 square. Let's minimize the d square. What I'm saying is that instead of calculating the minimum of d of y, I want to calculate the minimum of d square of y. And why is that? Because I'm claiming that the point y where d square is minimum is going to be the point where the d of y is minimum as well actually. D and square of the d behave in a sync manner. For example, let me just give you an example. So d and d square. So I'm saying that if d is taking big values, d square would take big values. If d is taking small values, d square will take small values. And if I assign a small value to d square, then d would be also small. And if the d square is big, then d would also be big actually. So they are kind of have a positive relation. So if d is 1, d square is 1. As d increases, d square also increases. Okay? So 3 and say this will become 9 and so on and so forth. And if d square is taking a big value, say 100, then d would also be big. And if d square takes, say for example, a small value, okay, then d would also take a small value. So they are kind of in a positive relationship. So instead of calculating the maximum of d of y, I'm going to calculate the maximum of d square of y. Why? Because in d of y I need to deal with the square root, while here it is just a polynomial actually. Okay, it's just a polynomial. Let's give this polynomial a name f of y, and let's try to find, for example, the minimum of this result actually, minimum of this function f of y, which is d square of y. So in order to find the minimum, what we need to do, we need to differentiate it. So let's differentiate. So when you're going to differentiate this, you're going to get 2 times of say y square over 2 minus 1 times with respect to y. So this is going to be 2y divided by 2 minus 0 plus this will become 2 times of y minus 4 times y minus 4's derivative, so 1 minus 0. So if you simplify this, what you're going to get? So this 2 and 2 will be cancelled and this will become say y square minus 2 times y plus this will become 2y minus 8. So if you simplify this, you're going to get y square, y cube minus 2y plus 2y minus 8. Okay? And y cube minus 8 and equate it to 0. So we equated it to 0. So once we're going to equate it to 0, the only real solution that you're going to get is y equal to 2. In other words, take the cube root on both sides and take the y equal to 2. And once you have this, then I want to check that whether this y gives me the maximum value or the minimum value. So in order to compute this, I can apply second order derivative test. Let's calculate second order derivative, which is going to be 3y square and 3y square actually. So in this, if I substitute for example 2, you're going to get 3 times of 2 square, so it's a positive number. So if it is a positive number, y equal to 2 is the minimum of, this f of y, which is d square y actually. Okay. So d of y has a minimum value at this number. Now, we want to find this point actually. So this point, in order to find this point, I need to find x actually. And how x is related with y? So x is y square over 2. So then if x is y square over 2, okay, x is y square over 2, now this is going to be 4 by 2, so it's equal to 2. So the 2 point is the closest to 1/4. So 2 point is closest to 1/4. Okay. This is what really is the point that we want. So we found a point. You are given a curve, and we wanted to find a point that is closest to that given curve actually. So the problem goes like this. Imagine we have a river. So this is a river in which water is flowing. Okay. And imagine, imagine that the width of the river is 3 kilometers. Okay, this is what the width of the river is. Imagine at a point near the, on say one bank of the river, one point of the, there is a person who is, for example, who is at a point say A on, you know, what do you call, one side of the river actually. Okay? And now this guy who is, for example, standing at say point A on this part of the river want to reach another point on the river. That point is really what do you call B actually. Okay? That point is really B. So the main question is this. The main question is this. How this person should move, okay, say for example on a boat, okay, how a person should move on a boat in such a way that he reaches to this point in a minimum amount of time. So this guy who is sitting at a point A with a boat want to reach to this point in a minimum amount of the time actually. Okay? Say additionally it is given. So if this is the point A, this is the point right in front of A is C actually. And say, you know, this is given that the distance between the point C and the point B is 8 kilometers. 8 kilometers. Okay? 8 kilometers. Now, what should be the best strategy that this person should take actually to reach to the point B in a minimum amount of, what do you call, time actually? Okay? Now we can have some guesses. So one possibility could be that, okay, he goes, say for example this way and then goes this way actually. Okay? So in that case, this person has to cover a 3 plus 8 kilometer distance, which is going to be 11 kilometers actually. Okay, this is one possibility. The other possibility could be that, okay, this person say should the other possibility could be that he, for example, so in 11 kilometer case, you know, the trouble would be that, okay, he's going to cross through the boat, but then he has to run from the point C to the point B. So he has to walk or run from the point B to point C actually. Okay? So that would be like boating and running to reach to the boat C actually. The other possibility could be that, okay, he boat, for example, directly from what do you call point A to point B actually. Okay? So in this case, how much distance he has to cover? So this like becomes what do you call a right angle triangle. So if you think carefully about it, this will become, say, so this distance will become square root of 8 square plus 3 square actually. So in other words, 69 plus 9, okay, which is going to be 69 plus 9 is going to be 78 actually. Okay, which is going to be 8 point something kilometer. Okay, 8 point something, because 9 is 81, so it's going to be 8 point something kilometer. So that's one way to, approach the point B. Another way to approach the point B, that this guy lands at some point, for example, in between C and B. So let's call this point as the point D. As this point as the point, what do you call, D. Come through this, what do you call, around the boat, okay, at the point D, and then run to the B actually. Okay, run to the B. So you have three possibilities of, what do you call, running, reaching to the point B actually. Now imagine that now the person decides that he wants to take this path. Okay, he wants to take this path actually. So he wants to run, he wants to boat to some point D and then run. Okay, he wants to boat to some point D. So he doesn't want to, for example, run too much. So you don't want to take this path, or you don't want to consume a lot of fuel to reach to the point B. So what he decided basically, that okay, let's run to some suitable point D, okay, between C and B in such a way, okay, so boat to this point D and then run between D and B actually. So now the key question is, where should he boat, okay, where should he boat between C and B in such a way that he takes a minimum amount of time to reach the point B actually. Take the minimum amount of time to reach at the point, what do you call, D. So he has decided to not to take this path, not to take this path, but he wants to take such a path to come to some point D and then run actually. The question is, what is the best location between C and D such that he takes a minimum amount of time to reach from A to B. So this is what really you want to do. Okay? Let's call this distance, now since we don't know this point actually, so let's call this distance x actually. Let's call this distance x. So if this distance is x, what would be this distance? The total is 8, so this would be 8 minus x. Total is 8 minus x. Now let's come to the, what do you call, model. Let's create an equation for time actually. The time, let's call this time t. The time that he gonna, take to reach from, say, A to B through this path is going to be the sum of the two times. The time to reach from, say, A to D plus the time to run from D to B. This is what it is going to be. Now the question is, what is time actually?